I'll be presenting my paper on understanding wide-angle images through different projection. Our idea is to revisit the undistortion method while preserving the full field of view and using a method that's widely used in computer graphic literature, a square-to-disk projection. We want our projection to be network agnostic, to be used by any model in the existence, and we show through zero-shot generalization on semantic segmentation that our model can generalize on unseen lenses. What we want to do is we want to take a wide-angle image, use distortion parameter to project it into a canonical framework, and then use any segmentation network on it. The idea is if I change the distortions of the input image, the distortions of the canonical framework remains the same. So the segmentation network will overfit on those distortions of canonical framework, and since they are not changing, it will be able to learn the geometry of different objects. We want two things from this canonical framework. One, it should be full field of view, as in it should retain the field of view of input image, and it should be network agnostic. Previous method, what they used to do is do undistortion using a crop method where they crop the input image and perspectively undistort. This provides network agnosticness, but it's not full field of view projection. One of the other method uses cube map, where we divide the input image into 5 different parts and undistort each of them separately and stitch them together to get an image like this. This is good. This is both full field of view and network agnostic, but it has severe deformation along the edges due to the flattening and stitching of the images, which produces degrading results as shown in our experiments. We propose to use elliptical grid mapping, a technique widely used in computer graphic literature, also by photographers, to dirty defish their images, where they take an input point on the image and map it back to the wide angle image using this equation. But this is not canonical. To make this canonical, what we do is we use the distortion parameter in the form of a curve between radius of projection and an incident angle theta. We sample the radial value based on this incident angle and the curve, and we restructure the output grid of the projection and map it back to the wide angle image using the same elliptical grid mapping formula. What it helps us with making the projection canonical. As I change the distortions of the input image, the distortion of the output image remains the same, and hence we achieve our tasks. And this is also network agnostic, since we are not making any changes in the network. This is just pre-processing projection step. The canonical framework looks something like this. We have a forward warping using a segmentation network, inverse warping, and a simple linear projection layer, which is a 1D convolution to the predicted labels. We perform semantic segmentation experiment on a panoramic semantics Stanford 2D 3D dataset where we crop different wide angle images. The idea is to create 4 mutually exclusive training distortion levels from very low to high, train on each of them separately, and test on all of them together to understand generalization. To do so, we use a uniform camera model projection which only has one distortion parameter psi ranging from 0 to 1. In this case, we show MIOU accuracy on y-axis and distortion levels on x-axis, where each number represents a lens, where we train on high distortion region as shown by the pink region, what the image is looking like this, and test on other distortions with images that looks like this. As you can see, the performance of baseline drops as we move away from training distortion, but our performance remains relatively flat. We also want to test on real world data set. This also mimics the performance of all distortion levels. We also want to test on real world dataset, as in Woodscape dataset, which uses polynomial projection and has 4 cameras: left, front, rear, and right. But all of those 4 cameras are nearly identical as shown by the distortion curve here. Hence, we cannot perform generalization experiment. We compare with Swin unit based model on absolute performance. As you can see, EGM perform better than any distortion aware network. We also show that we can leverage pre-trained model when we use convolution network like DDRNet and Cygnus pre-trained on cityscape dataset. As you can see, EGM perform better, and we can leverage large pre-trained model as well. Thank you.